Hey guys, how you doing? All right, so we're gonna go over properties of water. And I have not shaved in a couple days, so I'm looking kind of rough, but that's all right. Um, so there's a lot of information here, but if you wrote down the pretest questions, you can kind of see where these apply to. It's really not as much as you think. So let's go ahead and get right to it. So properties of water. All right. So properties of water, we got covalent bonding. Do you remember from early in the year when we talked about types of bonding? It's the sharing of electrons. It's not like sodium chloride or potassium, potassium fluorate or something like that. It it's something with two non-metals that kind of coming together, not a metal non-metal. Because of that, we have the prospects of having polar covalent bonding, which is an unequal sharing of electrons. And especially when we're talking about water, you end up with something that looks kind of like this. I'm going to draw, so here's an oxygen. I got two hydrogens here. Since the hydrogens both have a positive charge of 1 and the oxygen has a -2, it balances out. But these charges are localized, okay? The charges are localized, so we end up with a bond that looks like this, with an overall kind of positive end over here and a negative end over here. And so this water ends up kind of being like a magnet. Kind of like something like a magnet, right? So if you've played with magnets before, you know that they're polar. You got a north pole and a south pole. The magnet kind of works a similar way. Okay, we got a positive, negative end. Okay, a great example of a molecule with polar covalent bonds is water. Why is water considered polar? Well, I just talked about it, but let's go over it again. The oxygen atom holds electrons tighter than the hydrogen atoms. This causes the sharing of electrons to be unequal. Okay. Okay. Covalent bonding versus hydrogen bonding. Okay. Do you see like these hydrogen atoms? They are kind of sharing these. They're sharing the electrons. And in hydrogen bonding, you can kind of see that the positive end is bonding to the negative end of the oxygen, or the oxygen here. So the hydrogen bonding is something you see between two water molecules, and the covalent bonding is something you see inside the atoms. Just kind of remember that. Okay, water is the solvent of life. It is considered the universal solvent. That is the exam question. Sure you know that. Okay. A solute is something that's dissolved into a solution or solvent to form a solution. A solvent is a substance that devolves into solutes, and we kind of talked about this with the lemonade and all the other stuff that's in it. Okay, so here comes my famous glass again. It's a horrible glass, but whatever. Okay. So the water in my lemonade would be the solute or the solvent. That's going to be the solvent because all the other stuff goes in there, like the little lemon juice that's in there. I'm going to do red for the sugar. And my famous lavender is also going to go in there too, to make it lavender lemonade. Okay, iced tea is the example that I'm giving you, but also lemonade is another one. Okay, properties of water, some more. We've got cohesion, adhesion, and surface tension. This is some of the physical properties of water, or stuff that gives water its physical traits, but it has to do with stuff that's happening at the molecular level. All right, so let's take a look at it. Okay, cohesion, what does that mean? If you are cohesive, that means you like to stick together. Water is sticky for all three of these reasons, but cohesion means it sticks to itself, Water is attracted to other water molecules, so just remember this right here. Water likes to stick to itself. You want to probably write that down. Okay, that's what cohesion means, sticks to itself. Adhesion, water is attracted to other molecules. It sticks to other things. Adhesion. If you adhere to something, it means if you adhere to the classroom procedures and rules, please adhere to the rules. Well, that just means that you are sticking to the rules. Okay, so adhesion means sticks to others. And surface tension is the combination of cohesion and adhesion. Okay. Water is pulled together, creating the smallest surface area possible. Okay, and that's why this is possible right here. If you've ever seen a water strider or a piece of paper float on top of water, it has to do a lot because of the densities of the things, right? So how closely together the atoms can kind of stick together and the molecules can stick together means that it's not going to be very easy to break through that surface tension. Okay, that has a lot to do with the way that water attracts to itself. Okay, capillary action, properties of water. It's very fascinating. If you ever thought about how, there are roots down here, right? So these trees right here, see these trees? There are roots down here, right? Probably use a different color for the roots. Use green. Okay, now if you've ever worked with plants before, you know that you water, and the water goes into the soil, but then somehow all this water starts traveling up the root systems, and it somehow is able to overcome the forces of gravity, travel all the way up these trees to every single little leaf we've got here, right? Isn't that pretty amazing that it's able to do that? How is it able to do that? Well, it has to do with the fact that there are adhesive forces, cohesive forces, and that surface tension, right? So water acts kind of like a straw, and that's because it likes to stick to itself. If you've ever stuck a piece of paper, and I'll actually, here's my old copy right here. So I don't know if you'll be able to see this very well, but let's give it a shot. Right? Here we go. All right. Got this towel right here. If you can kind of see. Not really. But certainly this towel will get more wet as you go further up over time. And that's because capillary action. Okay, water likes to stick to itself. So as it hits the walls of a surrounding, you get that meniscus shape, right? So you learned probably in biology and every other science class you've ever been in that water will adhere to other things and it creates like this kind of bowed shape. And because of that, the water will attract to the sides and any other water will kind of follow its way out from the bottom, right? Your eyeballs work the exact same ways. You have like these little tear ducts right here. A little bit of water comes out and then boom, boom, boom. As the water travels this way, it attracts other water to be able to coat your entire eye. Without this, we really wouldn't be able to use the fact that water is the universal solvent to our advantage biologically at all. So all the things that are in the ground, right? All these dissolved minerals and solutions, they're down here. I'm going to go ahead and just do purple dots all over the place. And none of this is showing. So 1 second. See. Happens. Stop mirroring. Let's mirror again. All right. Okay. All right, there it is. Okay, so all these like purple dots that I'm putting here, none of these things would be able to travel up the root system if it weren't for the fact that water likes to stick to itself and to the walls of the tree. Okay, so I'm going to go ahead and show that since the sides of this purple stuff sticking to the tree, kind of like the straw, kind of like a meniscus, it will force these other particles to travel up to try to meet it, right? And this will happen for a while until there's too much water that groups together in its mass. Mass makes it such that the gravity, the force pulling down on it is more than the capillary action that this has with the wall, okay? So as this grip that the lavender stuff has on the wall becomes too weak for gravity that is pulling downward, it will no longer be able to hold itself up and it will start to fall back down, okay? But trees and such, they evolved in a way that the xylem, the little hole in the middle, has chemical and physical properties that it will let just enough water in So that way the capillary action can take advantage of adhesive and cohesive forces of water. That's pretty cool, right? Yeah, so all of our biological processes are able to take advantage of chemistry, right? The solutions that are in the ground, the solutions that are broken up in the ground, minerals, rocks, and all that stuff, because of the fact that water has these wonderful, wonderful properties. Okay. High heat capacity. I mean, you've heard me go on and on about this in class all year. Really, really cool stuff. Heat capacity is this C sub P, capacity of heat. And we use this in the equation M times C times delta T is equal to Q, heat, and that is this right here, where you can calculate the amount of heat that will be absorbed or given off in an interaction in thermodynamics based on how massive something is, the nature of how it is heated, or the thermal inertia, and also the delta T. Okay. All right. Okay. So think about it like this. If you've ever played with a sparkler before, or those like little 4th of July sparklers, super bright white, those sparks are hitting you all the time. You know, those sparks are thousands and thousands of degrees Celsius, but they don't burn you, right? So even though the delta T is really high in that spark in your skin, since the mass of those little sparks is so small, it's not going to change the overall heat of your skin. It's not going to do much to change the temperature of your skin. Now, water has a really, really, really high specific heat. And those of y'all who did vocabulary for me, you probably wrote down a table of specific heats, and I asked you to do water. Water is 4.18, rough, give or take, grams per what is it? Grams per degree Celsius, grams Kelvin, grams per degree Celsius. I'll have to get back to you on that, but it's grams per degree Kelvin or something like that, or degree Celsius, gram per degree Celsius. Yeah, gram per degree Celsius. So the amount, joules per gram degree Celsius. Joules per gram degree Celsius is what it was. It's an energy unit, kind of. Joule per gram degree Celsius. Okay. So it would take 4.18 joules to change 1 gram of material, 1 degree Celsius, or 1 Kelvin. If you look at some of these other ones real quick, let me see if I can pull up the browser real quick. Just look up some specific heats. I can't help myself. Specific heat tables. See what we got here. All right, here we go. It's not helpful. Those are just a bunch of weird solutions. Sapphire. Just go to the good old Wikipedia here. Hey, here we go. So you look at the heat capacity here. This is air, about 1. Makes sense. Look at aluminum. We're 0.8. Ammonia. Let's look at some of the ones that you're actually kind of familiar with. How about that? Here we go, copper. 0.38. So your metals that you are more familiar with, chromium, glass, gold. See how low gold is? Okay. So these things all mean is if they have a low specific heat capacity, it means they're going to be very easy to heat and very easy to cool. Okay, so they gain heat very easily, they heat up really quickly, but they also cool down very quickly. Water is 4.8. It's 10s, 20s, 30 times greater than some of those values you just saw, which means it's very hard to heat up. So if you've ever been out in the woods, right, even if you drive out to the woods from being downtown San Antonio, you'll notice almost immediately that it's a lot cooler. And why is that? Well, because of that picture we just looked at in the previous slide, where you had all those trees, right? Those trees, they have capillary action, they fill up with water. And because they're so hard to heat, it's going to make the surrounding air stay a lot cooler once that heat is absorbed, right? So if the energy it takes to heat up a tree, right? So if you heated up a tree 20 degrees, that means when the sun goes away, it's going to take a very long time for the water in the tree to release the heat back out to the surroundings, okay? That's why you might have noticed that when you walk around at night, after a really hot day. It's like, oh yeah, I'll just wait to go work out at night because the sun's gone. And sometimes you're like, man, I am like sweating up a storm and there's no sun. It feels almost more impressive than it did when the sun was out. And that's because the concrete had all that heat all day, but concrete doesn't have a very high specific heat. So once the sun goes away, the second law of thermodynamics says that the hot energy in the concrete is going to rise up into the cooler air. So you could actually end up with a much hotter evening than you expected because of the way that concrete absorbs heat. Same thing with buildings. That's why buildings made out of metal and stone and concrete, things like that. That's why the city stays really hot. It's almost like an oven, so when you turn off the light, the heat inside the material is going to leave. All right. So there we go. It takes more energy to raise the temperature of water compared to other solvents because the hydrogen bonds hold the water molecules together. Hydrogen bonds are pretty strong. Okay. This gives water a high specific heat capacity. And this is going to also change when you take into consideration the phase of matter that water's in. So when water is a liquid, obviously there's adhesive forces. But when you have it as a solid, it forms these crystal structures. And we're going to take a look at that in a second. And it's much harder to break those regular structures. Okay, water is less dense as a solid, and it has to do with the crystal structure. Okay, so if we look at and compare the, ice, the solid form of water, the liquid form of water, look at how much more. Hold on, this isn't shown. One sec. All right, let's see if we can get it to work this time. All right, there we go. Okay. So if you take a look at the solid form of water, we call it ice. You notice that there are these nice, like almost hexagonal patterns here, or pentagonal. Either way, you see these big holes in between. Liquid water, it's much more kind of free form, obviously free flowing. That just from like old school science. That they're not going to slide past each other very well when it's a solid versus a liquid. Because there are these nice holes here, when you take this ice cube out, what you end up having are holes that you can fill with air, right? O2 and other things, right? N2, O2, H2, all that. But either way, the important thing to know is that it fills up with air or some sort of gas. And all those gases from that table you just looked at, the specific heat capacity, have a really high specific heat, which means it's very hard to heat ice. The really nice thing about that is you can build these things out of it. So if you were somewhere really, really cold, you can build yourself an igloo, right? And that's why igloos will actually keep you warm, right? And you can even, they're so hard to heat that you could even have a chimney fire in there, right? So this is kind of an X-ray view now, right? And you end up with somewhere you can live and not die, right? In the middle of winter, in the tundra, right? And that's because solid ice, or solid water, known as ice, has these places where you can put little pockets of air in, which are hard to heat, right? That's a really nice thing about solid water. It also means that you're not really ever going to be able to freeze the bottom of a lake, right? Because what happens to ice, what happens to water, if you look at a really, really, really deep lake, what happens to water as it gets really cold? Well, bottom right here, it's going to get really, really cold down here. But as this gets cold, what does it turn into? It turns into ice. So that ice block right here will end up floating to the top because it is less dense than liquid water. And what happens when you get a layer of ice on the top? Well, the ice is going to act as an insulator, like an igloo, and it's going to end up insulating the lake. So it's very, very hard to freeze over a really deep lake. The lowest temperature to really get to the bottom is maybe 3-4 degrees Celsius at lowest, okay? All right, so let's go ahead and read the slide. Water molecules are bonded together in a solid. The space between molecules is fixed. So because it's fixed, you have a fixed amount of place you can put oxygen and stuff like that. Liquid molecules are constantly bonding and rebonding. Space is always changing, so it doesn't hold that space in between there. Okay, properties of water. Let's recap. The properties of water include adhesion. Do you remember what adhesion means? Does it stick to itself or to other things? Well, think of glue. It you use it as an adhesive, right? Which means you stick two things that are different together, right? Cohesion is like a group sticking together, right? Cohesive forces. Capillary action, we talked about that ability to kind of water to stick to itself to climb up things, right? Because of that adhesion to the walls and the cohesion to itself. It wants to stick to other things, and then it's going to like, okay, water, I'm up here. Yeah, water, I'm down here, and pull itself up, right? High surface tension means that it's hard. The space between molecules on the surface of something is really, really tight, so it's hard to break through. It holds heat to regulate temperature. That's a high heat capacity, hard to heat up, really difficult to cool down. Okay? It keeps its temperature well, and it's less dense as a solid than a liquid. Remember that water is polar, that hydrogen and oxygen, since they're kind of bent, it's a bent angular thing. Okay. Because of that, there is a big positive end and a negative end. So it acts kind of like the way a magnet does a little bit, and it's the universal solvent as a result. Okay, here's the universal solvent. So you can see that here is a block of salt, sodium chloride. Okay. And you can see that in the different bonds here, so here's chlorine ion, negative, and you can see that the bonding, the way that this thing kind of shifts around is a little bit different for each thing. Okay. The sides that are presenting themselves to the ions are a little bit different. Water can dissolve other polar substances, and due to its polar nature, it is also able to dissolve ionic compounds, such as salts like NaCl, calcium chloride, lithium bromide, etc. So these are all ionic salts, right? And they come in and they break them apart really easy. When it breaks down solutes into ions in solution, this is known as dissociation. The dissociation is what happens with these ionic compounds. When you do chemistry, this becomes important later. It tells you how many moles of solution you get, and it ends up being like 2 moles of each of these. You know, it's not like if you had 1 mole of sodium chloride, you end up with 2 moles of each at the end. Okay. All right. Well, that's all you need to know for right now. There might have been more information you need to know. But, you know, I think it's very interesting. You could teach an entire class on water and it wouldn't be a wasted class. All right. Y'all have a good one. All right. Blah, 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 blah.